From the Library of Congress in Washington, D.C.
I'm Peg Clifton, Research Specialist in the Science, Technology, and Business Division. Today, we launch the 7th year of our collaboration with NASA Goddard. It's my pleasure and privilege to introduce to you Dr. David Grinspoon, who will make the formal introduction of today's speaker, NASA astrobiologist Pamela Conrad. Dr. Grinspoon is the first holder of the Baruch S. Blumberg NASA Library of Congress Chair in Astrobiology. The chair was established in the fall of 2011 and is a distinguished senior position whose holder undertakes sustained research at the intersection between the science of astrobiology and its humanistic aspects, particularly its societal implications. Prior to his selection, Dr. Grinspoon was the curator of astrobiology in the Department of Space Sciences at the Denver Museum of Nature and Science. He is a well-known researcher in planetary science, the author of Lonely Planets, The Natural Philosophy of Alien Life, and tweets at #DrFunkySpoon. While in his position here, he is examining choices facing humanity as we enter the Anthropocene era, the epoch when human activities are becoming a defining characteristic of the physical nature and functioning of Earth. And he also happens to be on the science team for Mars Science Laboratory as co-investigator on the Radiation Assessment Detector, RAD, on the Rover. Please welcome Dr. Grinspoon.
Thank you. Good afternoon. Thanks, Peg. Well, I'm very happy to introduce the first speaker in this year's series of talks in the ongoing collaboration between the Science, Technology, and Business Division of the Library and NASA Goddard Space Flight Center. This is the 7th year of these programs on subjects in Earth and space sciences, and in addition to today's talk on Mars and the Curiosity rover, this year there will be programs on hurricanes, managing satellites, exploring possible other Earths, and finally, our place in the cosmos. Today's speaker, Dr. Pamela Conrad, Pan Conrad, is an astrobiologist and mineralogist with the Planetary Environments Laboratory at the NASA Goddard Space Flight Center in Greenbelt. She has worked for the past several years on the development of approaches and measurement techniques for assessment of habitability in planetary surface environments. Her planetary science interests include the comparative early evolution of Mars and Earth and the measurement of habitability potential on rocky bodies of the solar system. She is Deputy Principal Investigator and Investigation Scientist for the Sample Analysis at Mars, or SAM, instrument suite, which is presently exploring Gale Crater on Mars as part of the Mars Science Laboratory mission. Her extensive field experience revolves around characterizing the edges of the habitable zones in deserts, both polar and temperate. Since her involvement with the Mars Science Laboratory, Pan has become interested in the measurement of the noble gases and what they can tell us about planetary differentiation and evolution. Pan began her higher education journey with a BA with distinction in applied music from George Washington University, where she then obtained a master's in music theory and composition, and then a master's in geology, followed by the PhD in geochemistry and mineralogy. Please join me in welcoming Dr. Pamela Conrad.
This is kind of cool because I was at the meeting where we announced the first Bloomberg chair here in astrobiology when David got the award, so it's kind of a cool recursive thing here. This is my favorite topic, so I'm really happy that I get to talk to you about it. And it's a little bit tongue-in-cheek when I call it extraterrestrial real estate assessment. However, it really is that. because when you go to look at a prospective home, you think about your requirements. Is there room for a garden? Does it have a fenced-in yard for your dog? Is it near a good school? Can you get onto the beltway easily? Is it too noisy? And so forth. We do exactly that process when we try to define what the requirements might be for life, both on this planet and on another one. Sadly, we have no clue what life would look like on another planet, which is problematic because what's good for one is not necessarily good for another. So what we try to do when we do something so poorly defined is try to come up with those features of life on our planet that we think might be applicable to life elsewhere. So while we actually do our own exploration today, I'm going to do a few things. One, I'm going to talk a little bit about the requirements for life that I personally think might be relevant to life somewhere else. Two, I want to talk a little bit about how we approach extraterrestrial real estate assessment by analogy in the field on Earth. And three, I want to give you an update on what we're doing with Curiosity at Gale Crater. And if we can tie all of that together in a reasonable time span, I'm going to leave plenty of time for questions. I'm going to try not to talk too fast. And so if you see me flipping through slides quickly, it's because I want to get to the juicy bits so that you can talk as well. So you all probably know that we're on Mars, or if you don't know, surprise, we're on Mars. And it was a very difficult journey. I've been working on this project since 2004, when we wrote all the proposals for what we call the payload investigations. A payload investigation is not just an instrument that made it onto the rover and got selected for the team. Sometimes it's a suite of instruments, but it's also the set of experiments, things that we propose to the scientific community to do on Mars. And then by competition, the instrument teams and the investigations are selected. So writing such a proposal was very daunting. I participated in 5 proposals, even as the lead of one. One got accepted, and that's the one that I work with today, and I will, of course, be talking a little bit about it. And the primary goal of the mission, the reason why we're on Mars, is to try to figure out, does anything live there, or has it ever done so? And to do so, we have to compare it to Earth because we have a sample of one planet where we know there's life, and it's this one. And it's very difficult to, in an objective way, explore a system that you are within. So because we have no choice but to do that, to understand our own planet, if we can look outside of that, we actually, in a way where we keep changing our perspective, going inward and going outward and going inward again, we learn something about our own planet, and we learn some things about Mars by the things that we have learned about our own planet, and we just continue this process recursively. Now you can see just from the picture, I have to dumb things down for myself quite a bit because I came to science late in my career, and I'm not so good at quantitative things, so I do them pictorially. And the obvious thing here, but I should mention it for a specific reason, is that Earth is a lot bigger than Mars. So when the planets form, they accrete from the inside out. Little particles glom together and form bigger particles and form bigger particles and bigger particles, and the gravitational attraction of these globs of stuff holds the planet together. But when that stuff stays together, it gets heated up, and as the materials get heated up, the outside cools at a different rate than the inside. So what that means is the raw materials change. What they do is we call it differentiation. From the inside out, you get layers. So a planet is a layer cake, and what you want to know is the stuff that's on the inside available to the stuff that's on the outside so you can do chemistry? And the reason that's important is because if it does nothing else, the thing that life does is make new stuff out of old stuff, and when you run out of the new stuff to make products, you have to go in the other direction. In other words, you stop making new stuff. Now, we all can think of some obvious things that we as organisms make. aside from, bodily functions and that sort of thing, we make technology, we exhale particular gases into the atmosphere, we make new food for ourselves, we make a lot of stuff. So, when we look at Mars, we have to ask ourselves, what can we make on Mars with the stuff that's on the surface? Does that stuff on the surface exchange places with some of the stuff on the interior? And in that way, we come to a new question, which is, how dynamic is that planet? What's going on to exchange materials between the inside and the outside? So we turn to Earth first, and we say, okay, how do we characterize our own planet? Well, it's big, it's warm, it's wet, it's got a thick atmosphere. And one reason why we have that thick atmosphere is we have this robust magnetic field that keeps cosmic rays from coming down and frying us. Now, the thing about that magnetic field is this. It is generated because the insides of the Earth are roiling and twirling and swirling, and they are generating the magnetic field by their motion because of the physical properties of those materials. One thing we notice about Mars is it's smaller. Look at the color. It's red. That means something. Alas, it has no magnetic field. Sadly, because it has no magnetic field, it has lost a lot of its atmosphere by mechanisms that we don't all agree upon yet. We call it hydrodynamic escape in the major theory. Because we don't have too much atmosphere, we're kind of cold. The kind of water that can exist without having the pressure of the atmosphere to keep liquid phases in equilibrium with solid phases and gases at a particular set of temperatures, not so good. So we don't have a lot of surface water on Mars. And it's all because we don't have that magnetic field. So it seems like a physics problem that only the geophysicists might deal with would not be so relevant to the astrobiology that I'm doing, but in fact it's all connected stuff. So point number one for today's summary, everything is connected to everything else, but you probably already knew that. So we sent Curiosity rover to Mars to help us address some of the questions that would give us clues about whether it's alive or not. You already know what our primary goal is, but when you do a science project, you actually become a little bit of a systems engineer if you're going to do it remotely on another planet, and so you break it down into discretely addressable scientific objectives. And so the objectives that we have for this mission are to assess what we call the biological potential. Could you conduct the business of metabolism? Could you reproduce? Could you do all those things that we see as being consistent with life, at least as we know it, on another planet? To do that, you've got to kind of know what you're working with, so we want to understand the geology and geochemistry. Those things that rocks tell us are the book that gives us the window into the past on Mars. Only thing that we can look at on the surface in terms of things like water and air and that sort of thing are ephemeral things. What's happening right now? We can tell you the dynamic at the surface, but if you want to infer what it was in the past, we have to look into the rock record. We're also trying to understand what the role of water has been and continues to be, or not, in modifying the surface of Mars, because when we figure out what's happening, we can get an idea about, again, the dynamics. The dynamics is what we keep going back to time and time again, because life exists on a different time scale than the creation, the maintenance, and the eventual decline of a planet. So when you look in time, it's very difficult. If we're at a planet that's past its prime, or it hasn't gotten there yet, we're out of luck unless we know how to look for the signs of what is to come or what has been. So try to keep that in mind as we go back and forth about the rocks and the present environmental measurements. We're also trying to understand the surface radiation, and that's part of the experiment that David is attached to, the radiation assessment detector. That experiment is important because if we're going to go to Mars or even send more stuff to Mars, we need to understand how difficult it is to withstand the slings and arrows of galactic cosmic rays and solar energetic particles. Not to mention UV, because it gives everything at the surface of Mars a much greater degree of sunburn than we would get on Earth. So Curiosity rover is going to try to accomplish all of these objectives with 432 scientists all getting along and achieving consensus every day as we plan what we are going to do on a day-by-day basis. One reason why I'm able to come talk to you today is because the sun is presently in between Earth and Mars and we can't talk to the rover, so I'm off of tactical operations for another about 10 days. So let's go back a little bit to the basics about what makes a habitable environment, and then I'm going to ramp up the pace here. We know that there are certain chemical requirements. You need raw materials. We talk about the magic set of chemical elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Now, these elements are not the only elements that living things need, but these are found in everything that we know of that's alive to a greater or lesser extent. But there are trace metals and other kinds of things that are equally important. I don't have a font small enough to list everything that we need and still put this slide together, but you get the gist here. We need more than just the raw materials. We need energy so that we can do stuff with those materials. Remember that take old stuff and make new stuff? Or make new stuff and then make more new stuff. But anyway, we need water. Now, we don't just need water because it's a great solvent. Everybody talks about that part, but we need water for a couple of other good reasons. The types of chemical bonds that you can get with water are different. They're special, and we use those a lot in biology. We also need just positively charged hydrogen in biology. And what I like to think of as the primary importance of water, because we tend to ignore it the most, so I'm a defender of the underdog, is it is a fabulous thermal sink. Water is what we call infrared active. It absorbs infrared. That, by the way, is one reason why water is blue, because it's sucking up the red colors. Water absorbs heat, and it moderates the pace at which we exchange heat with the environment. We call that thermal inertia. So that's an extremely important reason why water is important. So you put these things together, and do you get a habitat? We don't know. There are some intangible things that make living things choose one spot over another spot. So the idea is to try to figure out what those things are. Sometimes it's a set of conditions. So I like to just refer to that as the physics of the environment. And some of that has to do with where you're fortunate enough to have been born. It's not such a good idea to be that close to Jupiter. It creates some problems, like asteroids flinging themselves at you and making giant pockmarks right in your favorite places near the equator. But also, the thermal environment has a function that has to do with how close you are to the sun, how often you switch what we call obliquity. As you go like this, as you're spinning on your axis, when your pole is facing more towards the equatorial plane or the plane that defines your path around the sun, you get a different set of climate conditions than you get when you're more upright like this. The dynamics, well, obviously this stuff we just talked about smashing into a planet is bad news if you're underneath the thing that's smashing in. On the other hand, it could also be good news, because if it's bringing new stuff you need, special delivery, to an extent, those impactors are good. And there is a school of thought that suggests that water was initially delivered to Mars, and possibly to Earth, by cometary sources. So, you know, you got to take the good with the bad, and maybe some of these impacts are good, but if you're underneath one, it's hard to argue. You mix that stuff up over time, and you get a set of events that happen that have to be untangled in what we call time-resolved measurements. You can take a picture of something today, but if it looks different tomorrow, that defines a sampling rate over which you must make the measurements. So we have to keep in mind while Curiosity is rolling that some things that we measure at one time of day may be different if we measure them at another time of day. So we have this awesome power supply. It is called a multi-mission radioisotope thermoelectric generator. Just think of it as a nuclear power source. So we take a nuclear source, we don't react it, we just let it decay and give off heat. We use that heat in a transduced manner to charge 2 big juicy batteries, and then every day we run off the batteries, we draw down the charge to, some extent that we define the day before, and then we let it charge back up to a certain extent before we resume operations. So this big juicy power supply enables us to make measurements during the winter and at night, and that's something we couldn't do with Spirit and Opportunity because we needed solar cells to run. So, big juicy power supply. Now the 10 investigations enable us to do things from a remote distance. We call that remote sensing, like take pictures, panoramas. We have a special laser zapper thingy that can send an infrared laser beam at a rock about 7 meters away for the maximum, maybe 2 meters close at a minimum. And we vaporize the material, making a cloud of plasma, which an optical emissions detector then can identify its chemical constituents. That's called ChemCam. We have things on our arm that we call contact instruments because we actually reach the wrist of the rover arm down and touch the rocks. We have 2 special instruments that live in the belly of the rover. I'm going to talk more about those in a minute, but they are an X-ray diffractometer and a suite of mass spectrometers called SAM, which is the instrument suite that I work with. And these instruments are distributed all around the rover. Some of the electronics is in the belly of the rover so we can keep it warm, and some of the stuff is mass mounted, as I told you, and some is arm mounted. I'm not going to have time to go through this bit by bit, but I just wanted to show you the picture of where the stuff is. And you see that thing on the front of the rover with those little circles, those 5 black circles? That is a near and dear to my heart piece of hardware because I made it. It is 5 cans that are hermetically sealed containing a silica brick doped with 2 organic compounds that are not found in nature anywhere. Why do I love this thing? Because this is the only thing we can drill with our sampling hardware on Mars that we already know precisely what it is. We have internal calibrants in our instrument, and some of the other instruments have calibrants. But this thing, you drill into it right on the front of the rover, just like you would drill into a rock. You process it through the whole sample processing system, and if you see weird stuff in this sample, you know that it is not in that sample, that it's either weird stuff that is indigenously from Mars or extraterrestrially, extra-Marsarily? Anyway, meteorites that hit Mars, or it's terrestrial contamination. So this is a very important calibrant for us. It's our only way of seeing whether our sample chain is clean. I told you I'd tell you a little bit more about the 2 analytical instruments. So the X-ray pattern, which is the thing on the left, is the first X-ray diffraction pattern ever taken on another planet. I'm especially fond of this, A, because I'm a mineralogist, and B, because my good friend Dave Blake is the principal investigator of this, and worked on this thing for more than 15 years in his basement, giving it off to friends when he lost funding, doing this and that to make it to Mars. And I want to tell you, it is so hard to persevere during times of shrinking and expanding funding cycles, getting your lab given away to somebody else, knowing that you've got other pressing needs, and this guy kept doing it, and now he's on Mars. That's a don't give up message. And the sample analysis at Mars instrument, I can tell you lots of stories about how hard it was for us to build our own instrument, but there we are, we're on Mars. So, what I'd like to talk to you about with regard to this is how we do our daily business on Mars. I'm going to skip this little bit of special stuff about our specific instrument, and I'm going to go first to this picture here. This is an actual photo. This isn't a drawing. When we landed on Mars, the heat shield separated, and we had this descent imager on the bottom of the rover. The bottom of the rover is just exposed to the atmosphere once we jettisoned the heat shield, and we took a picture of it, And the thing that's really cool that I want you to see, if you look at about 7 o'clock is where it's centered, you see that kind of gray slash? You're going to see that again. That's a dune field that's right near our landing ellipse. And you can see it with such exquisite detail behind our heat shield. It's really awesome. But that's not the only amazing picture we got of our landing. This was taken by the HiRISE camera on another mission called the Mars Reconnaissance Orbiter. And it is a picture of us dangling by our parachute as we were aerobraking coming in. The next thing that we saw that was a picture is our own damn shadow as we're sitting there on the surface of Mars. This came in very quickly, less than an hour after we landed, with the mountain in the background that we will ultimately explore. So the reason why I'm showing you all these pictures is to say that sometimes making a measurement is not a measurement that you can get quantitative about. You can only get a qualitative feel for where you are by looking at a picture. But if you'll notice how cool it felt to look at those pictures, that qualitative feel has a lot of intrinsic worth. When we do our daily business, we divide it up into different sol types so that we can model how much power it takes to do each of these things. And it takes a bazillion watt-hours of energy to do some of this stuff. I don't want you to read all this stuff, but I just want to give you a flavor for our approach, how we figure out what the heck it is we're going to do each day. A lot of it is determined by how much resources available to us in terms of time, data volume, sending stuff back and forth to Earth, or just the sheer energy, the watt hours. And each day when we get together, we start with a report on the rover health, and then different people have different functions, and we lead a big science discussion group that chooses what activity we should do. We only have a couple hours to agree on what we're going to do, and then the rest of the hours in our tactical cycle are spent actually writing the programs and getting the instructions ready and reviewing them again before we radiate the commands up to the rover, and then the rover does that stuff the next day. And we do this every single day, except during this conjunction time when we can't talk to Mars. And so if we want to get a weekend off, that means we've got to do 3 days worth of planning on Friday. So we haven't done a full weekend off yet. We had Saturdays off before conjunction, where we compressed the amount of time we spent on each day and went right to planning what we call N+1, the next day, or sol, as we call it in Mars language. The reason we distinguish between a day and a sol is because Mars rotates at a slightly different rate than we do. So a Mars sol distinguishes it from the Earth day. And because the rate of time is slightly off, ultimately you get to a time where an Earth day doesn't match up with a Mars day anywhere in the cycle of hours. And so then you just do a correction. It's kind of like leap time. So here's a list of things that we have debated with regard to what makes a habitable environment on Mars. I'm not going to go through these and read them to you piece by piece, because ultimately you'll get to see these on the website. But I want to put this here to show you that we have to ask a discrete set of questions in order to address the habitability issue. And you start with requirements, just like you do an engineering problem. What does life require? You gotta try to put your head there so you can figure out if the environment you're exploring meets those requirements. You know, remember about the good elementary school and the quiet and that stuff? So in the case of a planet, we're looking at things like the right chemical materials, the source of energy, the right physics of the environment. What can we measure about it that would give us a clue about whether or not it meets some kind of requirement for some presumed life? So I have developed personally a list of candidate measurements, which I've been exploring in extreme environments on Earth for several years now. And you don't have to read each one of these, but the point is I've divided them up into chemical measurements, physical measurements about the environment, geological measurements, and then some boundary condition geographic things. You don't make the geographic measurements each time you go. This is to say you take into consideration where you are on the planet. We, with Curiosity, are near the equator. That's going to give us a different set of things to look for and to ask about than we would be exploring if we were at the pole. So that is that boundary condition. There's another set of conditions which I did not put on this list, and we're not going to deal with it today, but it has to do with where you are astrophysically. Where is your nearest neighbor planet? How close are you to your star? Where are you in the evolution of your solar system, and so forth? If we were going to apply these principles to exploring habitability to other star systems, you would need to use that level of scale. Okay. So I told you we're in a crater. I told you we're near the equator. The name of the crater is Gale Crater. And the thing that is our ultimate destination is Mount Sharp, which is this, well, actually, it's officially called Aeolus Mons. It's in the middle of the crater, and it represents stacks, 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 and more stacks of sediment. And if you look at the drawing on the right side, which has got a kind of a cutaway cross section, you'll see the drawings of the presumed stacks of sediment. That's why we want to go there, because as we look at those layers, it gives us time. Each layer is a change in depositional environment over some time, and we think we'll get to see a lot of Mars history by getting to those layers. In the meanwhile, one of the things we're exploring is an area which is a basin where 3 different kinds of rocks come together, and the basin is at the distal end of something called an alluvial fan, which is a bunch of stuff eroding down that we can explore before we get to the more distal areas. This stuff gives us an idea that the rocks were deposited and worked underwater. The rocks that were deposited and worked underwater were observed on our way to our present location, which I'm going to show you in just a second. But I want to show you the approach. You take these pictures, you try to identify materials that visually look different, and that lets you know it's a different kind of rock. Then you start thinking about the properties of the different kind of rock. You can actually measure stuff like, thermal inertia, that thing that came up earlier. How fast do they change temperature? Can one kind of rock heat up another kind of rock and kind of moderate the temperature? That's important on Earth. If you're an organism living in Antarctica, in the sandstones of the Beacon formation in the McMurdo Dry Valleys, you get a lot of your heat from this underlying basalt, which gets really, really quite warm even in the middle of an Antarctic day. You can sit on it and it'll warm your buns. Where we are right now at this junction of these 3 different kinds of rock and this basin that I told you about, we loosely call Glen Elg. We have formal names and we have informal names, and we've got to come up with informal names because as you use the principles of the U.S. Geological Survey for mapping planetary features, they got to go through this process before they're vetted. But we have to know what the thing is that we're referring to on a daily basis so we can say, zap that rock over there or drill this one over here. So you'll see a lot of formal names and informal names, and they actually have a rhyme to their reason. We usually come up with a theme, we make a list of available names, and each day we select a name for a new target. When we look at the geological context, as from my chart of different kinds of things you measure, you see something interesting, and that is that the landscape defines different features, which in turn define different chemistry, which can make a difference to life on Earth. This place, which is in an area called Amboy, it's out in California in the Mojave Desert. This is a drainage plain. It's floodplain, and I drew that square. That's not naturally occurring. There's this one little tree there. Just one tree. Now, I drew the square to include the tree. If you look off to the banks of the floodplain, you'll see lots of scrub terrain. But the question that you have to ask yourself is, how do I decide how big an area I'm looking at? What is the meaning of that one tree there? Those are the questions we ask about that one rock there, or this or that feature that we observe on Mars. We ask ourselves the same thing about different types of terrain and other extreme environments. This is Badwater Basin on the top picture in Death Valley. Those are the Joshua trees just driving along the highway to get to Death Valley. They only like to live in a certain type of chemical condition. And that chemical condition is defined by elevation. So they need certain temperatures and they need certain chemicals, and if you get that, you get the Joshua trees. Same thing is true for the microbes in Death Valley living in this what we call evaporite rock. Water periodically inundates Badwater, and then it mixes the chemicals around. You see that skinny green line in that hand specimen? I don't know if you can get it from where you're sitting, but those are photosynthetic organisms, and they only live in that spot that deep under the surface of the crust and no deeper. And if you miss that one horizon, you've missed the living thing that's in that hand sample. So you got to keep stuff like that in mind when you're on Mars. So we have done 3 kinds of things. We've looked at stuff remotely and touched stuff. We've actually scooped up soil and ingested it into the 2 instruments, SAM and Chemin, that live in the belly of the rover. And we have now drilled a rock. And we've learned different things about the physical properties and the chemistry from each of these campaigns. Now we get the picture show. So the sand that we scooped is what we call a wind drift. It's fine-grained material. We think it's the kind of stuff that's blown around globally on Mars, and we measured it. We scuffed the stuff with the wheel because we wanted to know whether or not the rover was going to sink in like quicksand from an old-time Western. And as you can see, we didn't sink in, but we got a nice scuff mark of our wheel tread pattern. When we scooped, what we saw is that there's some very fine-grained stuff and that there's these little concretion things. And you see those little round things in there? That's what we call the armored part of the soil. We couldn't look at that just yet because the sieve that scoops and apportions the material into our inlet tubes makes all the materials that are bigger than 150 microns unavailable to us. So we haven't looked at that yet. We're just getting ready to look at that stuff sometime in the future. The picture that you see on the right shows you an important thing. The physical properties of the rock, and soil in this case, make a big difference. You see something about the processes that deposited the rock. That is the left panel of the picture on the right. You see those striations? They're called crossbeds, and that means that that rock was either wind-blown sediment or it was subaqueously deposited sediment, and the shape of those ripples in that rock will tell you which one it was. Look at that photomicrograph taken with an electron microscope on the right. You see those holes? Those holes are very important. You don't get living stuff living in the space between minerals in a basalt. The stuff might live in a crack, but the microbes can't live because there's not enough room, and basically when they make poo, there's no space for the poo to diffuse away, not enough porosity, and they would drown in their own poo. So pore space is important. At that level, you have to understand how the physical properties affect your ability to do metabolism, and that's what we're doing on Mars. Physical features. Physical features are everything from the temperature of the environment to the radiation of the environment to how often those things vary within the environment. Is there wind? What direction does the wind come from? How strong is it? Does it swirl around? We care about wind because if wind is coming from here and going to there, what we want to know is, the source of the material that's being driven in by the wind. So that's one reason. Another reason could be, there's wind. Oh, maybe we shouldn't deliver a sample into our funnel when there's wind. Oh, it looks like the wind is worse at 2 o'clock in the afternoon. Let's deliver the sample at 6 o'clock at night. Do you all remember when the Phoenix lander was near the polar regions of Mars and they had trouble delivering scooped sample into the ovens of their TIGA, or their thermal evolved gas analyzer? We learned from that. We made little wind guards for Curiosity. We studied the wind patterns. We only deliver at favorable times. So that is one reason why physics is important. But another reason is if there's a lot of wind, we want to understand the turbulence of air and how well the gases mix, so that when we measure the chemistry of the air, we'll get an idea whether it's representative of the whole planet, whether it's representative of this one little area here where smelly methane could be coming up, or whether it's not at all representative of anything because there's so much turbulence you can't tell. So that's a very quick and dirty overview of why you have to understand the physics of the environment. Let's take a look at this relationship here between radiation and the density of the atmosphere, or atmospheric pressure. this is one of the coolest things we've measured since we got to Mars. You see how those are opposite? That tells you that even that thin and weeny atmosphere is giving you some protection from radiation. And you see this perfect correlation between when the atmosphere is thicker, the radiation is less. So if you would doubt before the utility of this atmosphere, even though it's kind of thin, it is at least good for moderating some of the chemistry and the dynamics of the Martian surface. We have another kind of instrument that is on a principle of physics able to measure how much hydrogen is beneath the surface. Now we use hydrogen as a proxy for water. We could see hydrogen, or we could see hydrogen connected to oxygen. We call that hydroxyl, or we could see H2O or water. Of course, the other possibility exists that we could see hydrogen attached to carbon, which would mean we'd have big beds of organic stuff underneath the Martian surface. Now, while I don't think that is the case, we can't rule it out, and it's important to keep an open mind and not rule out any stuff that we can't definitively say is impossible. So this is called DAN, or dynamic albedo of neutrons, for the way in which we measure the hydrogen. This instrument shoots this stream of neutrons, which are fairly weighty little atomic particles, subatomic particles, and they come back to a detector. And how fast or slow they reflect off of the material under the ground tells you how much hydrogen is there. It's pretty cool. And so this shows you how well the instrument is performing based on a calibration test that we had while we were still on the ground before we launched. I'm not going to show you any DAN data to a great extent here because the way the plot comes out in tiny little histograms, it's difficult to show. Now I'm going to blast right through physics and get to chemistry. I saved that for last because we have so many ways of measuring chemistry. Again, I want to point out that the first blush at looking at chemistry is obtained by looking at the physical character from an image. One of the other very exciting discoveries we made was the effects of running water when we found conglomerate, which is a rock that gets only made by the weathered and rounded pebbles of things that have been aqueously altered. That was a clue that water was there. When we actually began measuring the chemistry, we saw that there was indeed a lot of water there. We also saw that there were other important chemical elements that would tell us that maybe it's not such a bad environment if you were trying to support life. You'll see this spectrum taken by the ChemCam instrument, a picture of a rock from which we were able to deduce that water had affected that rock, and that there was also calcium, and that there was some carbon, and that there was some iron and other things that might be relevant for life. Life has its own array of chemical elements, just like rocks have their own array of chemical elements. And this is one of the cool things you can do with geochemical measurements. You see the thing with the green and the red and the yellow line on the left? That is the pattern of chemistry associated with a particular rock. It's measured by a contact instrument called the alpha particle X-ray spectrometer. And it's just measuring chemical elements. You'll see across the x-axis on the bottom elements with an oxygen next to them. We tend to calculate in geochemistry things in what we call oxide weight percents. Look at this picture on the right side. So that's average terrestrial crust, average lunar crust, and a couple of other types, oceanic crust. But I got to show you this. This is cool. So this big one here, can y'all see that? That's the geochemical distribution of a photosynthetic bacterium. It's just what's on the surface and what you could measure by this method, but that is to tell you that just by measuring chemical elements, you can get a pattern that is distinct from the pattern of the rock stuff that is suspicious, and you can say, aha, that does not match the other rocks. It could just be a different rock, but it could be something else. You can measure the atmosphere, which is what our instrument SAM does, and we have measured the atmosphere since we got to Mars, and we now understand the major mixing ratios of important components so that we can understand what types of more reactive gases mean if they emerge from changes due to the seasons. There's a set of reservoirs and fluxes that we can begin to hypothesize about, and that allows us to speculate on what it would be like to observe an organic gas like methane, as we have done through observational astronomy. We have an instrument that is part of our suite, which is tuned specifically to look for this methane. Let's see. Okay, we're still alive here. 38 minutes and counting. So what we've done from looking at what we can see by the chemistry, the physics, and the environment lets us put together a picture. It's not 3 dimensions in terms of 3D space. It's 3 dimensions of thought space that allow us to approach the complex problem of habitability in a matrix sort of way, where we can say, check off this box, check off this one, check off that one, and oh, you check off enough boxes and you begin to suspect, this could be a habitable environment. So cutting to the chase in that regard, we have made a lot of observations about present Mars, and by looking into the chemistry of the rocks about past Mars, and what we have concluded is that we see nothing at this moment that precludes habitability on Mars. That doesn't mean we have found organisms or that we are saying Mars is inhabited. It means we are saying that we don't see a showstopper. So because we're only 8 months into a at least 2-year baseline mission, we'll be making many more measurements, and who knows what we'll find. Let me show you where we are right now. The rover landed where that blue writing is that says Bradbury Landing, which we named after Ray Bradbury, who had died just shortly before our landing. The end of that little gray line is where we are right now in a part that we call Yellowknife Bay. We have already drilled our first sample from the rock. This is what the bay looks like. We picked it because the rocks have a texture that looks like they were deposited underwater, and they're filled with veins, and those veins might tell us about some dynamic processes through which the rocks have been altered from underneath. We don't know. We're going to try and find that out. And as we picked targets, we drilled them and we investigated them with the ChemMin X-ray detector, X-ray diffractometer, and the SAM suite of mass spectrometers. And what we learned was that there was definitely alteration underwater, because we made a kind of mineral that we considered to be a holy grail of alteration under standing water, because that is a good preservation environment for organic molecules. You see how this is kind of hazy right there? That's a phyllosilicate, or the scientific name for a clay. The other thing that we measured out of this rock was a huge amount of water. You see where that says M18? That means mass 18. In our mass spectrometer, that's water. And so we're showing you that there's a ton of water attached to the minerals in that rock. So you already know that we're going to be going to Mount Sharp after we do more analyses. We're probably going to drill another hole and check out some more features of Yellowknife Bay before we get going on our long alpine expedition once our conjunction is over. But I want to just show you one more thing before we do the questions. And this is an open mind exercise. So when I was in graduate school, I had a topic called petrology, which is how you learn about the history of how rocks form and the processes and how they manage heat loss and so forth. And so the book we had was by this guy named McBurney. And I had a colleague come to visit me sometime later when I was working at the Jet Propulsion Lab at the time. And he said, "Oh, I see you studied using the McBurney book. Did you ever see the self-portraits?" And I said, "No, what are you talking about?" So he said every time he drew an image illustrating rock textures in a microscopic thin section, he drew a little picture of himself. So every page where there's a microscopic thin section, there's a picture of this little guy. And so, of course, I had to rip open the book and find the little guy. And sure enough, he was not lying. There is this little bald guy smoking a pipe on every page where there is a thin section. And the reason I am showing you this is to tell you that if you're not looking for the little guy with the pipe, you're not going to find it. So every time you look at anything, you have to be ready to expect everything. And especially if you're doing it by remote control on Mars, you have to make your brain very available to dynamic spinning. So I'm going to stop yakking here and let you ask some questions, and we'll take some tweet questions. And everything is fair game, and if I don't know the answer, you can write me an email, and I promise you I'll try to get you the answer. It's just pamela.g.conrad@nasa.gov, or you can just Google me and you'll find me. That's it.
I think I read recently that they're finding a lot of fluorine on the surface. Is that right?
Chlorine.
Chlorine, not fluorine? Okay. But they're saying that that's making it hard to figure out whether there was life or not. Is it something with the instrumentation or just not something you expected?
So the question is, do we have a lot of chlorine on Mars? That he was reading this. And so the short answer is yes, we see chlorine on Mars. And what happened was when the Phoenix lander went and did its 90-day mission, it detected a material called perchlorate. It's a very reactive material, but it typically exists as a salt stuck onto something else. Now the thing is, if perchlorate is globally distributed, that means something about the source of volatiles. You know, Mars has volcanoes. In fact, it is home to the biggest volcano that we have observed in the solar system, Olympus Mons. And so we know stuff has off-gassed from the Martian interior. So chlorine has been thought for a long time to be one of the volatile components in the interior of Mars. And we indeed, with Curiosity, saw the results of a chemical compound that contains chlorine and oxygen. Now, we are not saying it is definitively perchlorate, because it's hard to tell at this point. We have enough chemical evidence to definitively say it's an oxidized salt of chlorine. The reason why people point out that this might have a relationship to our ability to observe not necessarily life, but organic molecules, is because when we take something and we heat it up on Earth and we add oxygen to it, it combusts. So this is a source of oxygen. And the way we try to drive off the volatiles of solid samples is we do something called pyrolysis. We heat them up to high temperature. So the concern was, if you have this material called perchlorate on Mars, would it basically combust or burn anything that was an organic molecule? The short answer is we don't know the answer to that yet. The slightly longer answer is there are lots of chemical things you can do to determine whether or not the salt that we see is that or is some other type of chloride or chlorate. And stay tuned. Does that answer your question?
Yeah.
Okay. Yes?
How long did it take the Curiosity rover to get from Earth to Mars?
So the question is how long the commute took from Cape Kennedy to Gale Crater. And the answer to that is, in time, it took 8.5 months. And in distance, it was a very modest journey of 354 million miles. And it's not because we were 354 million miles from Mars at the time, but the actual path that Curiosity took, using the gravity of the different planets and avoiding other stuff, took it on that long journey. The distance and the time it takes to get to Mars depends upon the relative position of the planets, of course. So at different times during Mars and Earth's year, the journey could be favorable, lasting 8.5 months, or it could be not so great, lasting 2 years. So we hit it at a good time. And that's why NASA defines what we call launch windows, when the planets are close enough together that you don't have to burn so much fuel that you would need a humongous rocket to carry that much fuel to just, get you the right amount of boost to go into cruise. Yes?
Is there a high risk that something like an asteroid could come and disrupt the path of Curiosity, or just even take it out, different rocks kind of thing?
So the question is there the possibility, or at least is there a very high likelihood that an asteroid or something could basically hit Mars and either disrupt the path of Curiosity or And so the short answer to that is it's not a very high likelihood. There are different times in Martian evolution when there was a lot more activity in that regard. However, there are recent craters on Mars, and so Mars is still getting hit, and so are we for that matter. We recently had an impact that was not so gentle. And I think that the risk is quite low. I can't say it's zero, but
Are you monitoring?
are we monitoring space objects? We're always monitoring space objects, but it's very difficult to detect things that come in from particular angles and could hit Mars. That being said, we have 2 orbital assets from NASA, Mars Odyssey and Mars Reconnaissance Orbiter, that take images of the Martian surface. We can see things like new impacts, but seeing it in advance, Curiosity doesn't move that fast that we could really get out of the way if we saw something. Yes?
When you talk about terraforming, how long would you say it would take to create an atmosphere on Mars using, if say there's ice that you can turn into water vapor? I don't mean an atmosphere we could breathe, but to get beyond the 2% that's there now, maybe provide some UV protection.
So the question is about a concept called terraforming. There's a popularized concept, not just in science fiction, but a couple of astrobiologists, Chris McKay among them, who have advocated that you could modify the Martian environment so that it was hospitable to Earth life, making the atmosphere thicker, possibly allowing liquid water to run on the surface. So the short answer to your question is, I don't have a clue, because what you need to do is, if the atmosphere is presently still escaping or has escaped because of the lack of magnetic field, because of the lack of dynamics at the center of the planet, then you'd have to come up for a mechanism that would make up for that. The shorter answer is, ew. Because if we did that to Mars, then we would no longer have that part of the laboratory, which is a planet created at the same moment that has followed a different evolutionary path by which we can look at our own selves. So I would hate to lose our nearest neighbor holding up the bathroom mirror so that we can see our own reflection and figure out how we are evolving differently.
That's the whole point, right? One day we may need that other planet.
I think that all organisms explore as a way of looking for opportunities and threats in their environment. And at some point, we will explore beyond the Earth because we have to go. My thought is that we're not going to go because we destroyed our environment. We're going to go because we couldn't help it. So I'm not so worried about that yet. Yes?
There were some other devices placed on Mars. Are they still operating?
The question is about the other assets that have landed on Mars. Sorry for the NASA speak. I've been there now for enough years that it just flies out of my mouth. We call everything that we send on a mission an asset. The other rovers that are still on Mars now are first the Pathfinder rover, which was there in 1998. It was a little tiny thing, technology demo about this big. And Spirit and Opportunity, which are about this long and about this wide and about that high. So Opportunity is still sending back data, roving. Spirit got a sore foot, and she is no longer actively commissioned, but she's still there. And so those are still there. The landed platforms that we have sent, that is those things that don't have wheels and can't rove, the 2 Viking missions from the mid-70s, the Phoenix lander that went several years ago, the sad other things that approached Mars and landed vigorously. All of these are in the same category of it's a one-way ticket, because we don't yet know how to put together a mission with enough resources to bring something back yet. And we're working toward that. It's a very slow process because, for one thing, we have budget constraints. And for another, the amount of radiation hardening that has to be done to keep something going for years and years and years and years requires a lot of development on the front end and a lot of space qualification before you send it. So it's a one-way ticket for now. Yeah.
How long did it take Curiosity to move 1 mile?
How long did it take Curiosity to move 1 mile? So the bad news is we haven't moved a mile yet. And the reason why is because we are so nerdly that we have to stop and look at everything on the way. And so we've moved about 500 meters. So that's not that far, but we're looking at really cool stuff, and we just couldn't help it. Yes?
From what you've learned so far, what feature of Mars do you think creates the biggest impediment to life?
The biggest impediment to life on Mars. So that's a really interesting question, because right now I don't see an impediment that I would consider a showstopper. But if I were to think about life in terms of Earth life, the thing that I think is really important is to have a diversity of things you can do chemically. So until we understand what the diversity of chemistry is that's taking place on the surface or in the shallow subsurface, I won't really know the answer to that question. But I don't think there is a huge impediment just now. Yes?
What is the impact on Curiosity of wind, temperature change? So what's the wear and tear factor that affects the instruments? How does it do it? Do you have to make allowances for it and so forth?
That's a great question. He's asking what is the impact of environmental degradation on us, not to mention on the stuff we're measuring. And so when you develop a piece of hardware and you send it to another planet, you have to test it to 2 times its nominal lifetime. So the big impactors are 1, radiation, 2, radiation, and 3, radiation. That's a tough one because we have a lot of microprocessor controlled stuff, and it causes a bad thing to happen called single event upsets, which change your registers and how you retrieve and send data. So that is a concern, but we have radiation hardened materials, as do all spacecraft, so we hope we are mitigating against that. Also sun, ultraviolet light, it's harsh. And so ultraviolet light is hard on detectors that are CCD, or charge coupled device detectors, like we have in our point and shoot cameras and in our cell phones. They don't like ultraviolet light either. So beyond that, the mechanical threat always has to do with thermal cycling. We get hot, we get cold, we get hot, we get cold. Every day this happens. And so over time, you just stress materials and they degrade. So those are the 3 main things. Wind and blown sand is really not that big a factor. Yeah, that's why we got those lens covers. And don't forget to take them off before you take the image.
We'll take one more question, and then she'll take questions after.
So since, as you said, it's a one-way ticket whenever you have a Mars exploration project, but you can continue to gather data from most of the other rovers you sent for many years after their official mission span. How long do you think past, how long will Curiosity last?
Oh, that's bad. That's like trying to predict how long somebody's marriage is going to last. So the short answer is this thing is just amazing. I can't believe how fabulous it is that we're there and that we're working after all those years preparing. If Spirit and Opportunity were designed to last 90 days, and that was in 2004 that they landed, you can see that there is a good return on investment. I am not going to fall into the trap of guessing how long Curiosity will last and the return on that investment. All I can say is that I hope that if things move in a scalar way compared to Spirit and Opportunity, that it'll be my day to go out in a pine box before Curiosity is done, but I don't want to say that either because there's lots of stuff in the environment. But anyway, I think a long time.
Thank you, Anita.
My pleasure.
This has been a presentation of the Library of Congress. Visit us at loc.gov.